which was an ESA-funded project with the aim to produce a regionally optimized sea level product. And I worked together with a lot of other institutes like FMI, DTU, UCC, and DMI, and TUM. And well, the aim was to produce a gridded product based on advanced along-track altimetry data. And the outcome of this work is a gridded product, some sea level trend and uncertainty estimates, as well as the process along-track altimetry data. And I think that's a very nice demonstration of how you can combine efforts in advancing altimetry data in terms of retracking, sea ice classification, and gridding. So I'm going to quickly cover all of these innovations. And then I show 3 different application examples, what we could do with this data set. So why did we choose the Baltic Sea as a laboratory to advance sea level products? So the Baltic Sea has, first of all, very complex coastlines and many small islands and narrow straits. So it's pretty difficult to retrieve unperturbed information of sea level. So we used coastal sea level tracking to improve the data in the coastal zone. And also we have the occurrence of seasonal sea ice coverage in the Gulf of Finland and the Bay of Bothnia. So we also have to identify whether we're observing sea ice or open water or leads. So that's why it's a perfect laboratory to apply advanced pre and post processing algorithms. Here I list some of these innovations. So first of all, we applied an unsupervised waveform classification, which is done to discriminate between ice and open water and leads. That was done by Felix Müller. He has also a couple of publications on that, so you can check that. I'll show some links in the end. Of course, we applied coastal retracking, like the ACE retracker from Marcello Passaro. Also, we accounted for intermission biases using intermission cross-calibration, because we used many different missions here, like JSON, Crasat, Sentinel, Saral, ERS2, and so on. We have to reduce the offsets between these missions. And then we also applied an innovative gridding strategy on a relatively highly resolved grid with a 100-kilometer smoothing radius. And that data set is now well defined on this unstructured grid, as can be seen here below. We also validated all of these steps. For example, we checked the classification of sea ice in open water against optical images that can be seen on the left. And of course, we validated the data against tide gauges in terms of correlation, RMS, and trend differences as well. As one outcome of the study, we provide a new estimate of the mean sea surface, which can be seen here. And also, we see some improvements with respect to previous version, like the DTU 15, which shows, in particular in the coastal zone, some artifacts and some spatial variability. And if you look at the resulting mean dynamic topography, which you get after subtraction and the geoid, you see in some areas that we have smooth estimates, in particularly near the coast and behind islands. So that's a indication that we have better coastal resolution of the mean sea surface and hence the MDT than the previous product. So you can see that in near that island, for example. Also, as this data set is really useful for the analysis of trends in internal variability and potential drivers, we performed some investigations on the long-term sea level trends. And here on the left, I show the linear trends from altimetry as well as those from tide gauges. Of course, these tide gauges are corrected for vertical land motion here using a regional GIA model. And on the right, I show the trend uncertainties, and both variables agree pretty well. We also validated that. Show you a validation in another slide. And when we look at that map, we found that we see some really interesting pattern here, mostly that the trends are much larger in the Bay of Bothnia, so that's in the northern part, than in the southwest. So we performed some analysis trying to disentangle some potential drivers like wind forcing, which could have potentially caused such trend differences. Also, an average trend is slightly higher than the global mean sea level rise over the same period. Here, I just want to show a quick slide indicating the differences of our derived absolute sea level trends versus tide gauge trends. And we found that in our product, we provide more accurate information of absolute sea level trends than comparable gridded products for the same region due to the innovations in coastal retracking, for example. In our analysis, what might have caused this trend gradient across the basin, we found that this is mostly associated with anomalies in wind forcing, in particular, again, caused by variations in the North Atlantic Oscillation. And on the right, I show here a time series of the winter NAO, as well as a time series of sea level anomaly differences between the Bay of Bothnia, that's in the north, and the southwestern part. And we see that differences between these regions in sea level are strongly correlated with the NAO. And it's just likely a coincidence that, in particularly in the second half of the period of observations, we have more positive NAO phases, and a positive NAO is here associated with southern westerly winds, which causes water to be pushed towards the north, and that's why we see higher trends over the period of observation. But it's mostly a cause of natural variability and wind forcing, and likely not significant. As a third result, I show an experimental gridded product, which was used to demonstrate how this data can also be used to initialize models, used to predict storm surges, for example. And here we see the evolution of sea level during the silent storm surge in 2017. And this is based on the long track data, and we see some pretty interesting effects here because the Baltic Sea tends to oscillations in sea level. And before that storm surge happened, shown here in the middle plot, we had very high sea levels in the north, and that oscillated back and caused these very high sea levels then in the southwestern part of the Baltic Sea. And yeah, I think that's a very nice other demonstration of how the data can be used also to improve storm surge modeling. Finally, I provide here some useful links with information to the handbook, which describes all of these algorithms applied. And we also published a paper summarizing all of these results I presented to you. And for questions, you can also contact the Baltic SEAL team or visit the website. And there you can also access the data. So you just give some information and then you can access the gridded product. So it's a monthly product. And we also provide all the long track files of all the different missions if you want to work on that. And also on the website, you find some useful Python scripts to show manipulated data or plot the data, for example. Starting from here, we expect synergies with other investigations, like focusing on a sea level budget, for example, and there are already studies incorporating other variables like salinity and temperature, focusing on the steric variations in the Baltic Sea, and they have also already used these sea level data. Of course, the Baltic Sea is generally a very nice study area for validating absolute sea level trends because we have really a very dense GNSS network necessary to correct tide gauges. And also we have seen some other studies focusing on improving wave height and coastal altimetry grids. For example, I think Marcello and Marie have just recently published a machine learning-based gridding approach, and that was also all motivated by all of these efforts. So I'd like to close this description of the data set, and if you have questions, yeah, either write the Baltic Sea team or ask right now. Thank you.
Any questions for Julius? Okay.
Thank you. During the storm event that you were looking at for your storm surge, did you see the oscillation signal in the tide gauges and at what frequency? And then I was also curious if there is wave data as well.
So this analysis was done by some colleagues at DMI. So I'm not really the expert. So I would have to check that with them, but I assume that usually they use tide gauge data for sure to initialize these models, and very likely you would see such a strong signal in tide gauges as well. But I have to check again. And the second question, like if you provide data on wave height, I think so. Marco, do you know exactly what's in the data? Can we provide that?
It's hard to remember that, yeah.
Yeah. Possibly. But I think so because it's estimated, so wouldn't make sense not to show it. But I can check this again as well. I'll let you know. But not on the grid. That's what I know for sure. So only on the allometric data.
Hey, thanks. This might be a stupid question. Can you go back to your main C service?
Yes. Further back.
Yeah. Okay. Back one more. Just a comparison between the two.
Yeah. Well.
Yeah. Okay. So this looks very different. And then if you flip to dynamic sea level.
Yeah.
That's the same thing, just without the same geoid removed, right? So the scale bar is different. I'm not sure how they're so different from just a subtraction versus the original.
Yeah. Yeah. Good question.
Yes.
I mean, the scale is different here by one order of magnitude. So that's why it's pretty hard to see in this plot, at least.
Yeah. Okay.
Yeah. No, you're right. Yeah.
Okay, thanks a lot, Julius. Okay, so our next speaker is David Cotton, project manager of many ESA projects on the Altimetry. I'm going to share.
Thanks, Marco. Good afternoon, everybody. So yeah, I've got two talks, one after the other, on a couple of projects, two projects we're currently working on. So the first is the Hydrocoastal project. They're both about SAR altimeter processing. So Hydrocoastal, funded by ESA under the Science with Society programme. And the idea is to look at the junction between a coastal zone and inland waters, and to look at new approaches to processing SAR and SARIN data at that junction from PRASAT2 and Sentinel-3A and 3B. So looking at new processing algorithms, seeing if we can generate a continuous data set as possible, joining together rivers and coastal zone. So we've, the team, you can see the logos from the bottom right-hand side, there's 15 partners. We implemented a number of new processing algorithms, new retracking algorithms for solar altimeter data, developed them, tested them, and from that, evaluated them, and from the best performing, we've generated a global scale, or we're in the process of generating a global scale data set. And from that data set, we're then running a number of case studies to assess those products in terms of the beneficial, their improvements on what's currently available. So eventually there'll be 2 data sets available. There's a data set which we generated from the outputs of 6 different retrackers, and then a final product which is, as I say, using the best of those, best performing of those to generate a larger scale product. So well, it says 5 there. So we've implemented these 6 retrackers. Some of them were specifically developed for inland waters, some for coastal zone. But what we've done is actually the ones for inland waters we also applied over to coastal zone, just to try and achieve that continuity that I was talking about. So I'll give you a little bit of detail about what each of them involved in the next few pages. But in the data set, basically, we've taken the output from all of those, we've put them together in a merged level 2 data set. So all of the outputs from all of the retrackers are available together with the interpolated original ESA level 2 product. And if you want to know more about the algorithms, they're all described on the website. So there's what we call an algorithm theoretical basis document, which goes into quite a lot of detail about how they all work. So there's the 2-step analytical processor for ImageAdsat, which is essentially based on the Samosa model. And if we get a good fit from the Samosa model to the actual measured waveform, then we can get range significant wave height sigma 0. If not, it's a bit like the Samosa Plus implementation, where the significant wave height is set to 0, and you fit a specular waveform to it, and then you just get range. So the idea obviously behind that one is it can move from the coastal zone to inland water type specular reflections. There's the DTU space multiple waveform persistent peak retracker, which is designed for waveforms where there are multiple peaks, and the objective is to avoid snagging from off-nadir reflections. So it looks at adjacent waveforms, picks out the persistent peaks, and then retracts the persistent ones, and we're going to get range from that. There's the STARS statistical retracker that University of Bonn have implemented, and Luciana can give you detail about that. But it essentially partitions each complete altimeter waveform into sub-waveforms, retracts those, you generate a cloud of solutions, and then you analyze that cloud to derive a final estimate for each location. It's an iterative process, but you get range, significant wave height, sigma 0. That's a coastal retracker rather than an inland one. There's the AILS Plus retracker by Marcello Passero and his colleagues. So that uses a sub-waveform from the SAR altimeter echo, just picks out essentially the main peak and windows around that, truncates the waveform, retracts that, applies this, it generates its own C-state bias correction, and retrieves a range, but not significant wave height. There's this ICCR along track processor, which deals with multi-peak waveforms again. It looks for the peaks, removes some, only keeps the persistent ones, classifies them, and then retracts them. And then we have one SAR-in mode retracker just for CRASAT-2 data, which was only applied to the AGNC, which Aerosys implemented for us. So we implemented all of those retrackers. We processed them over 18 regions of interest, most of them for 2 years, and some for 3 years, where we were doing river discharge estimates. We used CRASAT, FBR baseline D data, and Sentinel-3 level 1A data. We used enhanced wet and dry troposphere corrections that Joanna Fernandez and colleagues at the University of Porto generated. And we generated this test data set with outputs from all of the 6 different retrackers on. So those are the different regions, just in the table on the left, and you can see them on the right. So roughly half and half coastal zone and rivers. So 2 years data for most of them, 3 years data for some, the ones in red, and just 1 year of data for the Caspian Sea. The idea was to look at a number of different kind of environments and regions so that we could assess how well the different retrackers performed in different situations. So that data set is available, except we haven't integrated the long track retracker yet, but we have output from 5 retrackers in it with the improved wet and dry troposphere corrections. And it's available either with just the level 2 output or a full one, which includes all the waveform stack information, which you can see is at least an order of magnitude bigger per product than the other one. Yeah, there's information available online, and it's on an application called Mega Drive, which basically, once you get the URL, you can just access this directly. So the panels on the right of the screen show there's Crowsat-2 data, either reduced or full waveform, and Sentinel-3 data. And then if you click under those, then you get to different regions, and then you click on the different regions, you can get down to the individual products. It's a long track data. So why might you be interested in accessing data? Well, you can directly compare the outputs of these different retrackers, see which type of retrackers seem to perform best in different environments, which retrieve more valid data. The closer to the coast you get, maybe the more complicated the topography gets. And then if you wanted to evaluate your own retracker, you could use the waveform product to generate something equivalent. So what we did, next stage of hydrocoastal, was we evaluated that first test data set. We saw, from our point of view, which algorithms perform best or overall. And so for the coastal zone, the University of Bonn STARS type retracker gave us the best results. And then for inland waters, the DTU algorithm provided the best results. And what we've done is we're in the process now of generating a global scale coastal and river data set with those 2 algorithms implemented. In fact, we're using the DTU for both the coastal zone and the inland waters on a virtual machine provided by Earth Console that Marco kind of described a little bit earlier. So we've got parallel processing capability on it, and then enables us to run a lot of data very quickly through it. And that's set up with this NOR sponsorship opportunity. So this global data set is being produced now. As it says there, level 2 data sets for the coastal zone and inland water, and then some time series for the rivers of water level and then river discharge. And then we're also producing an experimental data set for the more challenging smaller rivers and tributaries. We expect that's going to be available in 1 or 2 months' time, essentially, once we've completed that processing. So for that, if you're interested in accessing it, just I think there's an email a bit later on, and we really just want to know who's using it, and then we'll just give you the URL and you can get in there. So for this second product, at the moment there's 18 initial areas which we're processing, so we can carry out some case studies and assess it. As before, Sentinel-3A and 3B, and the complete missions up to the end of September last year, and then Cryosat-2 SAR mode only for baseline D data, so that's available up to the 21st of August 2021. So produced in a net CDF4 format. What level 2 enhanced is what we're calling the product. It's basically got enhanced because it's got the output of several retrackers on it. These are the extra areas we're looking to process next. We're basically just going to see how far we can get down this table before we run out of time and money. So the project finishes in June. If there's some areas in there that you're particularly interested in that you'd like us to kind of bump up the table, then let us know. If there's not areas in there that you would like us to process, then let me know again, and we'll see. Basically, we'll have a priority list, and we'll see if we can put that in or make a case to do some additional processing. I think that's all for the hydrocoastal one.
Thanks, David. Any questions about the hydrocoastal project? Okay. Okay, so I think we can move to your next talk, David.
Okay, and so the second one is about fully focused SAR processing. So it's about evaluating the potential of fully focused SAR altimetry for coastal monitoring, together with some river level gauges that a French company called Vortex have developed, which tell you a little bit more about later. But basically, they're easily deployable. They're very kind of they're small footprint and a kind of new approach to this. So the objective of this project is to, I would say, look at how fully focused SAR processing might be beneficial in a coastal monitoring system. And we're looking at two different environments in this case. One is the Severn Estuary in the southwestern UK between England and Wales. So there's this is a highly dynamic environment. It's got very big tides, very big tidal currents, quite strong flows out of the River Severn into the Bristol Channel. And the second one is the lower Rhone Delta and Camargue in the south of France. Very different, a low-lying flat river delta, a wetland environment, which is susceptible to inundation and from precipitation coming down off the watershed, and also rising water levels at the coast. And together with the fully focused SAR processing, we've installed new micro water level gauges from Vortex, two in the Bristol Channel area in the Severn Estuary and two in the Rhone Delta. So here you can see the two areas, on the left the Rhone Delta and on the right the Severn Estuary. So the Severn Estuary is a slightly larger area we're looking at. The Sentinel 3A and 3B passes, using again level 1A data from Copernicus and D2U space. So Heidi Randall and Karina Nielsen have implemented the SMAP fully focused SAR processor and started processing data for those two regions. And it's very flexible. You can determine, choose a number of options on how to process, including the number of looks you use, looking at the best resolution for getting the best results, and then get the water levels by combining the output of that from with the level 2 data from normal processing. So focusing on Severn Estuary, the ultimate objective is to provide a long track data for all of those tracks, and also time series data for a number of locations on those along those tracks. So far, DTU primarily processed data from one track, which is the 265 Sentinel 3B here, and we put in new gauges at Newport on a road bridge on the River Wye, River Usk, as it comes down. And then we put one on the end of a pier, a Western-super-Mare. So they're new gauges. And then the first processing, you can see the outputs from that on the right. So you can see how the actual position of the track varies from pass to pass. So that obviously affects the retrieval in terms of how well it meets the end of the river as it comes out into the estuary. And what was got out was these the heights on the right from the different passes. And originally they thought maybe they were capturing the bathymetry at low tide because there's very high tide, and that was they wondered basically if that was we were seeing here. But in fact, what we were getting was snagging from off nadir reflections. So after those get back. Yeah. Sorry. So those tracks were those heights were retrieved using the OCOG read tracker. But then there are various options, and so when we looked at retrieve, you can get up to 10 peaks out. So then when we looked at the levels from all 10 peaks, we found that actually you could retrieve the true water level along track, and you can pick out all of these off nadir reflections. And what you see is the black dots are the peaks from the 10 peak read tracker. The red diamonds are basically the fully focused default processor, the OCOG one, and the yellow diamonds are the 20 Hertz products. So you can see how the kind of default processing snags, picks out off nadir reflections, and you need this kind of 10 peak processing to pick out the true water level. So using that approach, DTU then generated processed that track for all of the data we've got from the beginning of the mission, and compared that to tide gauges at Newport, and not the ones we put in because we only put those in last year. So, but compared the process data to Newport tide gauge and the Hinkley Point tide gauge, and this is what they got out. So we got once we looked at all of the peaks, we improved the agreement with the tide gauge data with originally an RMSE of 3 meters from the OCOG read tracker, and it came down to 1.2 meters. So there's still clearly a lot of improvement to be got, but it kind of demonstrates the difficulty in working in these highly tidal environments and getting good data out. So we that's as far as we got with the Severn Estuary data. Just begun looking at the Rhone Delta. As I say, it's a very different environment, low-lying river delta with wetlands, and you can see this rectangle essentially demonstrates the cross-track width, and you can see how it can potentially pick up reflections not only just from the nadir point but from various points across track. So that there are a number of surfaces within the altimeter footprint making extra noise. And our initial look shows that what we tried to do in the Severn isn't going to work for the Rhone, so we're going to have to look in more detail at the best approach for using a fully focused SAR processor there. The new in situ gauges are also part of the data set. So we've got two installed at the Severn Estuary, one at Newport and one at Western Supermare, and you can see the time series of the data here. The Western Supermare one dries out at low tide, so that's why you get this flat bottom to it. You can see the range there from 22 meters to 8 meters. So there's 16, 17 meter range, 10 meter range in tides in the Severn Estuary. And then the other two are in the Rhone. These two locations here are hardly any, well, as you'd expect, in the Mediterranean. The signal is more driven by the river flow. So the data sets we have, will be available, but not fully available yet. So we'll have fully focused SAR altimeter data, pass by pass along track data, and then time series at selected locations where the tide gauges are. Basically sentinel data since the beginning of the missions of 3A and 3B. And then we've also got the new in situ data from those 4 tide gauges, that 4 vortex tide gauges, those 4 locations. They're available online at that URL there. It's not fully functional yet. You can get the in situ data, but we haven't finished processing using a fully focused SAR data yet, so that's We expect that to be a couple of months until that's available. This is just the last one. So this is just what the website looks like. So you go click on either one depending on which area you want to look at, and then you can zoom in and extract the data. There'll be, in the end, so this is just one example track. In the end, there'll be you'll be possible to download data from individual tracks, and you can also click on there to get the tide gauge data from each location. Okay, I think that's all. Thank you.
Thanks, David. Any questions?
Yeah. Why do I think it's too much? Well, it's still large. Obviously, I mean, I think we'd be hoping to get down to tens of centimeters ideally, but yeah, it's so this is, I think they found the most highly correlated point rather than the closest point. So they were not sure a little bit.
So you bin the data and you find the time series which is the best.
Yeah.
Okay.
But it's because, as I say, the tidal range is enormous. You can see from there it's over 10 meters from its springs. And then, although the gauges are, well, the new gauges are set up to take measurements at the time of the overpass. I think any difference in terms of the time of the overpass and the fact that it's not exactly co-located is going to generate that big RMSE.
So it must be the tide, the different tide. You correct for the tide? No. You correct the data from the tide for the tide? No.
No, well, no, it's
So kind of on this point, I was wondering in this comparison, because the gauge is slightly spatially distant from the track, did you correct for any phase shift in the tidal propagation?
No, so this is kind of an initial validation, if you like, just to see. It was mostly to see which way of processing the fully focused SAR data was best, to see what improvement we could make. So it might be possible to improve that validation. You can see that they're pretty bang on in terms of where they are located in terms of the passes. But I think even if you look at the positions of the pass from pass to pass, I'm sure that would that's start introducing errors as well. So you could do quite a lot of detailed modelling and work out how to improve things.
Okay, and let me add a detail. We didn't use a specific retracker for the inland water domain. We are using the multi-PTR retracker provided in the SMAP processor. And this is a multi-PTR retracker which allows you retracking up to 10 peaks in the waveform. And that's why the measurements were very dense, no? Because actually they allowed us to understand the persistent, the persistent range, and to understand the water level. Moreover, it's Sentinel-3, so there is these issues. There is this issue with the replica that will surely have an impact on the standard deviation of these results, and also the contamination that can happen. And so it's about considering many things, and surely the fully focused SAR retrieval will improve in the future as retrackers tailored for the inland water domain will be developed. Okay. Okay, no more questions, so we can move. Is time for coffee now, or one more talk? Okay. Is 10 to 3. Okay, So time for coffee. We meet in 20 minutes, right, Jerome? Okay. See you in 20 minutes. Thanks.